Okay, good morning. Can any of you hear my voice?
Good morning, sir.
Thanks. Okay, I think we're quite ready for the discussion today. Let me test again. Can any of you hear my voice? Hello, can any of you hear my voice?
Yes, it's on.
Okay.
Yes, sir.
Okay, thanks. Okay, good. So I think today's discussion, we will move on to the next chapter where the single degree freedom system is again considered. However, today discussion, I think we will consider what they call the force vibration, the case in which the system subjected to the external force. Previously, in chapter 3, what we concern is about the vibration of the system without any external force, just the free vibrations. In terms of mathematics, we call that system as the homogeneous system, the system that the differential equation system that on the right-hand side, you don't have any term, any excitation term, and equal to 0. That is called homogeneous system. And the solution of that, the solution of the free vibrations, mathematically, we call it the homogeneous solution. We have learned that before. Today, we will consider the system on the figure you see, single degree freedom system, but today we have the external force F. Like this, right? We have the external force F acting on the mass. But for sure, for the dynamic system, we prefer to look at the external force that is the dynamic force. Since if the F, the external force F, is a static force, like the dead load, the self-weight of the structure, those kind of force is static, right? They are static, and the result is very simple. If you have the static force, remember, if you have the static force, the response becomes something like this. F equal to K multiplied with X. This is in the static equilibrium. It's like that. But in more general form, we are known about the dynamic equilibrium already. And the dynamic equilibrium is take the form like this. When the force F is a general force of time t, it can be both static and dynamics. for sure. You see, if I assume my force F of time t as in equation number 26, become a static force, of you know that the system don't have any velocity. The system don't have any accelerations, right? It's static. Static implies you don't have the movement. I mean, the velocity and the acceleration. The movement x you can have, the deformation, for example. But you don't have any change of the movement, like the velocity or the acceleration. That's why you can imagine that when the term of x double dot equal to 0, x dot equal to 0, you got the static equilibrium F equal to kx. That's it. That is story about the static analysis that I think you have learned a lot in structural analysis, subject or courses. But today with me, in equation number 26, you see the force is a dynamic force. And to make the system be in equilibrium with the external dynamic force, the system behave with the velocity and the acceleration. We found the movement of our system under the dynamic force such that it contains some velocity and accelerations. And considering those systems, by looking at the equilibriums that we have discussed before, I think I asked you to cut the spring here, to cut the dashboard there, and fill the force equilibrium, right? We do the force equilibriums, write down the free body diagrams of the mass M, and end up with 26 before. Today, we will look at this kind of form, the force vibration. Let me call it the force vibration. The force vibration is directly, the meaning is very clear, right? That means you have some vibration under the force, under external force. Is not equal to the free vibration. The vibration without any external force that we have learned in chapter 3. This is chapter 3, right? But today we are talking about the force vibration. Equation as in equation 26. However, when we look at equation 26, we found some difficulties, at least if you have the knowledge of the second order differential equations for mathematics. Solving equation 26 normally is very difficult, except some special kind or type of force. It depends on the type or the shape of the function ft. Whether the function ft is a complicated function or easy function, easy mathematical function. Since if the f of time t on the right-hand side of the equation 26 is very, very complicated function. Forget about solving this 26 analytically. What you have to do is to use what they call the numerical techniques. to approximate the solution. Solve the system numerically, not analytically, because it's too complicated. But if the f of time t on the right-hand side of 26 be some special function, some easy functions, mathematically we can solve it analytically by hand. And one of the form of the equation f of time t that is look quite easy to be solved, and at the same time we found some physical applications, is the harmonic function. That's why today we start the force vibration system with we begin with the harmonic functions. We will assume on the right hand side the force of time tf of time t here on 26 be a harmonic force function. And once we assume something like that, the vibration that we obtain from the force that be a harmonic force function will be called the harmonic force vibration. That is the name of this chapter, chapter 4. Okay? So solving equation 26 for today's discussion will assume the form on the right-hand side f of time t to be a harmonic functions. But before we get into the detail, I think it's quite common to be known that the general solution of equation 26 is the combination, right? It's a combination of the two parts of the solution. Since you have to solve the equation number 26 and obtain, I don't know, something like let me do this, something like this. Assume that the x of time t, the solution of this equation 26, need to be the part of the homogeneous solution plus the particular solution, right? And the harmonic homogeneous solution is the solution belong to this equation, and this one, the particular solution belong to the first equations. Okay, please don't be doubt about this, because this is second order differential equations, and when we solving the differential equation, everybody can imagine that you need to involve the integrations. Solving the derivative, you need the integrations. To get the x, you need to perform the integrations, and every time you perform the integrations, you end up with the constant, arbitrary constant. And since this is a second order, you need double integrations 2 times. You need to perform the integration 2 times, and this integration 2 times, you can expect to have 2 arbitrary conditions from your solution, in your solutions. And the solving of equation 26 directly to guarantee that the left-hand side equal to the right-hand side, you solve only the x sub p, the particular solution. And in the particular solution, you don't have any arbitrary constant to taking care the 2 initial conditions. That's why we need to combine with XH or the homogeneous solution. And by using this superposition, you see is no doubt, is no problem, right? If you put the plus sign here, let me do this for you. You plus the XH and XP together from this equation, and that equation, the summation becomes something like this, right? Still equal to FT, no problem. So please don't be confused. why we need to solve this too. And if you still don't really understand, please take a look at the mathematics, the chapter called the solving the differential equations. Okay, that's why in this paragraph you can see that we mentioned about the homogeneous solution, and the particular solution, the combinations of these two terms, your solution become the complete general solution that contain arbitrary two constant to taking care of the initial conditions of your system. Okay, so we will look at equation 26, but before we try to solve this equation, let we define the harmonic force together. The harmonic force is the force that contains the sine or cosine term mathematically. And this can be represented by, I don't have the equation, maybe equation 26a. Let me define this as 26a. Okay, so it's just the F0 sine big omega t. F0 is the amplitude of the force, it's just a constant quantity. And the big omega is a circular frequency of the force. Okay, so right now you have 2 omega. When I say or mention about omega, please remember you already have the small omega. This small omega is not the big omega, is a property of the system you have, right? Let me do for you the small k and the small m. So the small omega or the omega, I often mention omega, mean this small omega, okay, is the properties of your system, of your building. It's nothing related with the force. Okay, it's a property of our building itself. Whether it has the natural frequency when we move the roof of the building a little bit, maybe 10 centimeter, and release, let the building go back and forth by itself. It's a free vibration, right? No external force acting on them. And the way they go back and forth, fast or slow, is defined by the frequency, natural frequency of the system itself. And for the single degree freedom, you have only 1 degree freedom. You have only 1 frequency for the system. And that is governed by this equation, the small omega equal to square root KOM. If you increase the stiffness to your building will go back and forth faster because the frequency is higher. On the other hand, if you increase the mass M to your building, the building will move slower. It's move back and forth, but slower. This is because of this omega. Okay, the small omega. But on the equation 26a, the big omega is defined as the frequency of the force, not the building, of the force. So the force that acting on your building, the frequency of the force will be fast or slow is dependent on this big omega. Okay, so it's become something like that. And on the right hand side, you can see the drawing of the force. I just try to plot the force with time t, and you can see the harmonic force is just a sine function, changing the amplitude, always changing the magnitude with time, and the amplitude, I mean the maximum force is F0, right? And the minimum force is the minus F0 on the negative and positive. Okay, like that. And the period of the force is the big TF, and it's equal to 2 pi over big omega. Okay. The next is To solve equation 26, let me make it. Oh, it's too far. Okay, no way. To solve equation 26, so we start with the force with as in equation 26a, we introduce 26a into 26 and we obtain 27. So this is the governing equation of motion of your harmonic force vibrations. And to make the right-hand side equal to the left-hand side, if you have learned about the differential equations before, you can imagine that we have to assume the form of x so that it make the left on the right to be equal. And for sure, on the right-hand side is a psi function with the frequency of big omega t. Therefore, on the left-hand side, I'm pretty sure that we need the same frequency of the vibration to make the left-hand side equal to the right-hand side. When I say with the same frequency, what I mean is this. You look at the force, it's like that, right? How about the response, x? If I assume the response x of time t to be something like this, vibration like this is time t. What do you feel? Can you make the x like this, the red color, to be exactly equal to, of course, I have to multiply with k, I have to plus cx dot, I have to plus mx double dot, and make the thing to be equal to the blue part. No, sorry, the pink. You see, if this one and that one have the different frequency like this, it seems impossible. Remember, when you look at equation 27, every parameter you multiply or you subtract, right? You make the summation, you plus sign. You cannot change the frequency. Once you cannot change the frequency, how come that one can make the left-hand side with the high frequency? The red color have higher frequency than the pink. For sure, you can look and see, right? If the time scale is the same, I plot on the same time axis. So it seems impossible to make that the left-hand side and the right-hand side of 27 to be equal. The only thing that could be possible that make the left-hand side and the right-hand side to be equal is something like this, right? I have to go with the same frequency, no matter it's starting from 0 or not. But I think you have to go with the same frequency. I'm sorry that my drawing is not so cool, but it could be something like this. Okay. If your x have the same frequency with the force, now it's possible. I can make sure that the left-hand side and the right-hand side at every time instant, every time step, both of the, left and the right-hand side can be made equal. That's why the form of the solution X is in equation 28. You see on the term, we cannot assume that X is a psi function, pure psi function or pure cosine function, but the combination of them. At least the combination of these terms, sine and cosine term as in equation 28, guarantee the frequency of the X to be a big omega. But the phase is quite different, right? You can imagine this one, this equation 28 is exactly the something like this. The y, maybe I say y0 sine big omega t plus or minus 3. I often use minus here, alpha. Yeah. You make a summation of the sine and the cosine with the different amplitude. What you end up with is the new amplitude y0, but it's go with the harmonic function with the same frequency big omega, and the phase shift, we call this phase shift alpha. Something like this. Okay. Hope you can prove this because it's quite how do you say, sine a plus b or sine a minus b. If you have learned from the high school, I think you can expand the term, right? And you can prove the thing like this. Okay, once we assume that the form of the solution of 27 x of time t can be represented by equation number 28, the summation of the sine and the cosine term. Introduce equation 28 back into equation number 27. You can see on the pink color, right? My handwriting, that once you introduce the things like this to the displacement term, to the velocity term, you have to perform the derivative on x before, right? And introduce to the c multiplied with x dot. And I hope that you can do the same thing with the x double dot term. And once you introduce 28 into 27, I think you can imagine, right? On the left-hand side, you have many terms now, but all of the term will contain sine and cosine of big omega t. And what you have to do is to make the left and the right hand side to be equal from equation number 27. You have to say that, okay, every terms that contain cosine big omega t need to be 0. And every terms that contain sine big omega t need to be equal to f0, because the right hand side is show f0 multiplied with the sine big omega t. With these two conditions, okay, set equal, the cosine term set equal to 0, only the coefficient of the cosine term, okay, set equal to 0, and the coefficient in front of sine term, okay, set equal to big f0. With these two conditions imposed on you, you can solve for y1 and y2 for sure, and this is the result. Then you obtain y1 and y2 from those two conditions that I mentioned before, as in equation number 29a and 29b. Okay, so you obtain this. And once you obtain this one, you can introduce this equation back into equation number 28. But the form of 28 is the form of you have sine and cosine. So it's not easy, at least for me, that if you want to ask me, what is the maximum displacement under the external force F0 sine big omega t as in equation number 27? It's quite difficult. If I look at equation number 28, you see the amplitude, the displacement term is defined as the summation of the two terms, sine and cosine. For example, if I know y1 and I know y2 is equal to maybe 1.7 and y2 equal to maybe 4.5. What is the maximum displacement of my building? It's not straightforward to answer, right? It's not easy. I have to do some manipulations of the mathematics about the maximum quantity from the two terms of sine, cosine, the summation of them. But if you can write down the solution of the 28 by using number 30, it is easy, right? It is now very easy to answer. If you ask me, what is the maximum displacement of the building? I would say the maximum displacement of your building is a big X sub P. Okay, just coefficient, because we know that the sine term is return something in between 1 and -1. Therefore, it's not cause any effect on the response, the amplitude of the structure. The maximum displacement is mainly how to say, mainly influenced or controlled by the big XP. So the form of 30, equation number 30, is more, how to say, natural, right? It's more practical for engineer to be applied. Therefore, most of the time, we prefer 30 than 28. But I don't want to use 30 introduced into 27 because it's more difficult. It's easy for us to do derivative on sine and cosine term. But if you have the sine a plus 1 like this, it's a little bit complicated, right? More complicated than just the term of sine, cosine, like in 28. That's why we assume the form as in 28 because we want to solve 27. Very easy than 30 when solving 27. But once you obtain the solution, it's more practical to change the form to 30. That's why this is a practical form that most of engineer, almost an engineer prefer. Okay. Introduce the Y1 and Y2 to make the compact form as in 30. I think you can end up with the parameter xp become the square root of y1 square plus y2 square and equal to that amount, right? Very complicated term again. And the phi p is the arctan of the minus y2 over y1 and it's equal to arctan of the 2 per sine big omega over small omega or over 1 minus big omega over small omega all square. Okay, as in equation number 31. And okay, so we end up with this. This is the end of the solution. We already obtained the solution, x of time t. But remember this one, it just guarantees that the left and the right will be equal if your solution x is the one as in equation number 30. But in equation number 30, you see the term xp is nothing contain arbitrary constant. You don't have any arbitrary constant here. Phi p also is determined from the frequency ratio between the force and the natural frequency of your building and the damping. No arbitrary constant. To taking care initial condition like initial displacement, initial velocity of your building at time t0, for example. Therefore, this is just guarantee that the left and the right hand side of equation 27 will be equal if you introduce x like this into 27. And this is the solution of that. But the problem is it contains nothing about the arbitrary constant to taking care of the initial conditions. That's why we need two arbitrary constant terms to complete that. we combine the homogeneous solution in two. That's why the total solution, the general total solution, become as in equation number 32. In 32, you see you have the particular term on the right-hand side. Look at the second term on the right-hand side. It's a particular term. And the first term is the solution from chapter 3, exactly. The homogeneous solution from chapter 3, the free vibration solution. Okay? And look at these two terms. It seems that the first term on the right-hand side will be smaller, smaller, smaller with time. Because of this, right? Because you have the exponential power minus t minus ct alpha t, something like this, right? So this will make the whole term become smaller, smaller. I mean the first term only. Smaller, smaller, and smaller when t approach infinity. But on the second term, we don't contain, it doesn't contain any decay term, decay function as in the first term. Therefore, when time is increased, most likely the second term will control the solution, since the first term becomes smaller and smaller with time. But the second term is keep steady. They don't decay with time, but they don't increase with time as well. It's just steady. Just go back and forth, back and forth, back and forth with the same amplitude like that. Keep like that forever. Remember, the XP is a constant. And the sine term is return you just a plus and minus 1, plus minus 1, like that with time. That's why you look at equation number 32, they mention only the second term, particular term, since the effect of the first term will be smaller and smaller with time, right? So you can remove this term out from your consideration. For many applications like that. But mathematically, strictly speaking, your solution, complete solution, total solution, has to be 32. You have to combine both terms. Okay? So this is a plot of the solutions under one particular initial condition as well as the forcing function. And you can see that the total x, this is a total, the total response x, I'm sorry, xt, which contain both homogeneous and particular under the harmonic force. But on the below, you can see this is the extract of the part of the homogeneous and the particular solution respectively with time. Of course, the combination of the homogeneous XH and particular XP will be a total solution. The effect of the first, the homogeneous term, you see, is decay with time. This is a free vibration, becomes smaller and smaller. But please be noted that this example is the underdamped system. With the damping ratio, I think maybe 5%, something like this. It's the normal case of our building. A particular term you see on the last plot is just the harmonic function. Okay, so the summation of this will make the system to be vibrate a little bit not steady at the very beginning. Maybe this to that. And the name called is the tangent response. And after the tangent response, what we found is something very steady. That means the effect of the homogeneous solution or the initial condition is already zero, right? No effect. And the vibration at the steady state is controlled by the XP, by the particular solution only. Okay, that's why many engineers just consider only this part, particular solution, because it's happened like that, like this in many applications. But I try to show you this figure with some intention, like in this case, because I apply the initial condition, very big initial condition. So the peak or the response of the total response at the very beginning during the tangent vibration is pretty high, comparing with the vibration during the steady state. But this is because I provide the system with a very large initial conditions. That's why the energy at the very beginning is very high. Then the effect of the harmonic force later. So the maximum displacement is controlled, is found within the tangent response period. But normally the system is not like this. The system mainly is like when your building is hit by the earthquake, or your building is hit by the typhoon, or the very high wind force, something like that. Your system starts from less, from zero. But if your system starting from zero, the thing could be something like this. Let me draw you the total response. It could be something like this. Okay, I'm pretty sorry that my drawing is not so cool, right? But you see, the tangent response is from here to there. And this is the steady state. This is a transient. So the maximum displacement, the maximum velocity or acceleration, the moment and the shear force will be controlled by the steady state mainly. That's why many engineers concern a lot about 32A, not 32. Okay, this is because the effect of the first term, the harmonic term, will be quite small comparing with the particular terms. But during the exam, or if I ask you the total response, I need from you the combination or the summation of the two terms. You cannot remove the first term. Unless I say I ask you to consider only the steady state vibration. If I ask you so, you consider only the second term as in equation number 32A as your solution. It could be okay. So, okay, let me consider one of the example, and then I think I will quiz you somehow about this. The AF, okay. Look at this. The example. Let's consider a simple single equilibrium system again. The mass is 5,000 kilograms. And there's the external force Ft acting on the mass directly, as in the figure. And you see the column stiffness is given. The viscous damping is assumed to be 4% and subjected to the harmonic force of 20 psi big omega t. The unit is kilonewton. And find the response of the system if the big omega is 25 radian per second with zero initial condition. And find the response. B, calculate the response of the system for plus 30 millimeter initial displacement. And C, calculate the steady state response of the system for big omega equal to 30 radian per second if the F0 is fixed to be 20 kilonewton and the initial displacement is assumed to be plus 25 millimeter. Okay, let's do it step by step, one by one from A to C, okay? Starting with A, find the response of the system when big omega is 25 radian per second with zero initial conditions. Look, I have to introduce, I have the property of the K, right? You can compute the K, you know the precise, you know the small omega is the square root of K over M, right? F0 and big omega. Once this information is on hand, I think it's quite easy to compute. You start to compute XP, right? And VP. The XP and VP is this one, right? This one, right? 31, equations 31. You just introduce this term, big omega over small omega. This one, we call the frequency ratio. Is the ratio of the forcing frequency over the natural frequency of your building, circular frequency. I know the F0, I know the K, I know the big omega, I know small omega, I know psi. So every parameter is known to you now. You can compute the constant big XP and VP. And I think if the computation is correct, it could be something like this, right? You would obtain the big XP equal to 0.021, remove 7 for me because that one is not the good representing the displacement. It's too small. If you go with millimeter, it could be enough in terms of civil engineering application. We don't care much about the micron, nanometer, or something like that. It's too small. You just remove 7 and 7 there. The VP equal to 0.313 radian. Okay, and then we will compute first, then second, compute X hash and phi hash. Okay. Okay, at this step, I would say something to you, some of you. I have found many of my students previously confused about this. They often feel that if the initial condition is zero, if the initial conditions are zero, the homogeneous solution will be zero as well. The idea like this, or the understanding like this, is quite okay if you're talking about the free vibration. No doubt, you don't have any external force. And if you also don't have any initial condition, your solution need to be a complete zero. XH be zero, VH be zero, I agree. But if You are talking about the force vibration. You're talking about the force vibration. Even though the initial conditions of the system are zero, initial displacement zero, initial velocity zero, but you cannot say that the xh and phi h will be zero as well. You cannot say so. And this example show you that it's not zero. Why it's not zero? It's because the xp, remember the total solution contains the two terms as in equation number 32. When we say the particular solution, when we obtain the particular solution, the second term of the 32, I never say in any condition before that the second term of xp, the green color, will be zero when time equal to zero. We never say so before. Who can guarantee that? That the second term, the green color, will be zero at the time t equal to zero? No. What we guarantee is only this, that the green terms, the second term will be guaranteed that if you introduce into 27, if you make the left and the right of this equation to be equal. But never say that when time t equal to zero, my term, the green term, will be zero too. No, never say so. That's why in the example, if you introduce the time t equal to zero on the second term of the particular solution, there is a quantity remain to you, not zero. And even though you see the initial condition, the displacement at time t0 is set to be zero, but you still have the xh and the phi h this time, not zero. Do the same thing with the velocity. Set the velocity equal to zero and perform derivative on your total solution and introduce time t equal to zero. Of course, you know everything about the particular part. The particular solution is known to you already from the first step, right? So the unknown to you is only the homogeneous solution, and only two constant is unknown, that is xh and phi h. You would have the two unknown now, xh, phi h, xh, phi h. And I do think you have two solution, two equations, two unknowns. You can be solved this. And after you solve this one, you will obtain the xh and the phi h as in these the quantities, right? xh equal to minus 0.02 and phi h equal to 0.346, something like this. Okay, you solve step one, you already obtain step number two. Why don't now you write down the total solution, because you know everything. So the step number three is just say that your total x is the summation or the combination of the homogeneous solution plus particular solution. And that's why you obtain this solution as the answer for the equation A. Okay. Question B. They just ask you to calculate the response of the system again for the different initial condition. We have the 30 millimeter initial conditions as in here, right? When it says something like this, it's implied that the velocity is zero. Initial displacement only is applied to the building. So at time t0, the velocity of the building can be set to be zero. Okay. Try yourself. It's not so difficult. Just change the quantity here. I think this one we change to 0.030 millimeter. Okay, 3 centimeter is here, right? And change this one. Not change. This one, the velocity is zero. The displacement is 0.03, and then you solve for h and phi h again. That's it. Okay. Next is about the equation C. Equation C, they change the frequency. Previously, the frequency is 25, right? But now we change to 28 and 50. So this one is not so difficult, right? Because they ask you to solve only for the steady state solution. So you just compute from step one only, right? I'm sorry, particular solution, the big XP and phi P. Once you obtain big XP is here, 0.061, and the phi P, I'm sorry, this one, they don't have the phi P. It's better to say something like that. It's more complete, right? Okay, if you want to make your solution complete. In the exam, if you write down the thing like this, of course, you can get the high score, but it's not 100%. If you want to get the full score, it's better to do this completely, like calculate XP as well as the VP, okay, and introduce to your solution. But my point here is something like this. If you compare the result you obtain from this example, from number 1, number 2, number 3, it changed a lot. When we change the big omega. So it implies that the frequency has a very, very high effect on the response of the building, the frequency of the force. And that's why we will consider about this issue together. This one, we show you that the forcing frequency is has a very high influence on the vibrations. Look at this part, you can see if your forcing frequency, I think the forcing frequency ratio equal to 1.1. Okay. There's a term already on the figure below. If the forcing frequency close to 1 here, you see 1.1. This is the case, 1.1 is there. The response is very high, very large, comparing with the two frequency ratio of 0.55 and 2.55. When I say the frequency ratio is this, is the ratio between the big omega over the small omega. If it close to 1, it means what? It means that your force that acting on the building has the forcing frequency close to the natural frequency of the building itself. And when this frequency close to 1, what we have noticed is that the response of the building become very, very large, comparing with other frequency ratio. In these figures, I can imagine that if the frequency ratio is 2.55, the maximum is just 1 point something in terms of amplitude of the response. But if the frequency ratio close to 1, you see in the figure, it go to a very high number, 4 point something, right? This one is very small. This one is also very small. The amplitude may be here. And for sure, when we have the feeling of something like this, as a civil engineer, we keep asking ourselves, what is the order of safety factor you have in hand? We often dealing with the design code that allow the safety factor in our design. Many design code put the limit state design, ultimate strength design, the load factor that we often employ or adopt in many international design code is in between 1 point something to 1.2 until 1 point maybe 7, 1.8 at most. That is a safety on the loading. And another partial safety on the materials property is about the reduction of the strength. We often found something like a reduction of the, I think, the columns. When you compute the nominal capacity of the column, we should multiply with the 0. Maybe 6, 5, 6, 0 point something, maybe 0.5. Okay, let's say 0.5. So in total, the safety factor that we have in hand, I think, is not greater than 3. It's about 2 point something to 3. But look at this. If my computations is not good, I design my building against this amplitude, just 1 point something meter. But in reality, if the force that acting on my building change frequency, my building response will go to 4 point something meter. That is allowed 4 times than what I expected or what I used in my design. No doubt, you can expect the collapse of your building. Okay, that's why the subject of dynamics is quite important to civil engineers, because the effect of dynamics is not just a small thing in which we can take care by our safety factor. Don't be worried about the dynamic load. You don't need to care to taking care of that, because we have the safety factor of 3. Even though they have the dynamic behavior is not beyond 3 times of static displacement. I'm afraid to say something different, that sometimes it's greater than 3, as you can see in this figure. However, this is very, very special case in which the force is harmonic. We consider the real or actual earthquake or the actual storm or wind force. We don't find the pure harmonic in there. We found just some similar. You imagine the earthquake, right? You shake back and forth to your building. even though it's go like a positive, negative, like the harmonic, but it's not pure harmonic. It's more complicated form of the signal or curve or force function. Therefore, maybe the magnifications of those force is not 4 times, 5 times like this. Maybe just 1 point something, 2 point something, maybe. It depends, right? We don't know exactly what would be the next earthquake that will hit your building. No one knows. But for sure, it's not a pure harmonic. It's similar to harmonic, it's not pure. Okay, we will discuss about this later, but at least for today, I would like to clearly mention to you that the effect of the dynamics has significant effect on your design. And that's why we don't really be able to assume that the effect of dynamic is too small. We can neglect, we can omit. We just taking care of the safety factor of 2 already. We don't care much about the dynamics. No one can say so. And that has the, how do you say, the design code as well. Today design code asks the engineer to do the dynamic analysis when you deal with the dynamic force. That's why we have the discussion together, right? To discuss about the dynamic, you have to learn about the dynamic, making your knowledge clearly understand about the dynamics so that you can obtain your solution or your building motion under the dynamic force correctly, accurately enough for your design or evaluation. Okay, that is about the effect of the frequency, and we can see that the frequency make an important parameter that can make the vibration to be small or large. The second plot is the plotting show the effect of damping. And this effect, you see, depend on the damping value. If your damping is 5%, is the largest curve, right? The largest, this one, 5%. The amplitude is quite high. If you change the damping, increase the damping of your building to 10%, you get smaller vibration. And if you can have the damping of 50%, the vibration is very, very small. Okay, this is the way I fix the frequency. And I think I fix the frequency ratio to be like a 1.1 maybe. And just change the damping and plot the 3 cases of the 3 dampings against each other as in these figures. Okay, and I think this one I assume the damping equal to 5% per side. Okay. Next is about the DF. Let me quiz you first. Okay. Let me explain you about the DF. I would like to finish this part and then perform the quiz. Right? It's 11:40. It could be enough time. Okay. Let me consider about the XP. The XP is what? The XP is the amplitude. Define the amplitude of your steady state solution. And it is defined like this, right? Epsilon over K multiplied with the 1 over square root of, you see, 1 minus beta square, all square plus 2% beta, all square. Of course, beta is the frequency ratio, big omega over small omega. There is one parameter we often say in civil engineering application as well as the mechanical engineering application, which they try to change the form of X become something like a S0 or ST. Let me see, X0. X0 multiply with the DAF. Something like this. What is X0? X0 is the F over K. F0 over K is a static, equivalent static displacement, right? F0 is just the amplitude of the force. If you divide by K, it is static displacement. When I say static, equivalent static displacement, it means what? It means if your force is not the dynamic force, it's just a static force having the same amplitude of force, F0, then your response or your building displacement will be equal to X0. Okay, and it's calculated from F over K. Very simple like that. The DAF is the term that taking care about the amplifications. How much the dynamic effect will amplify your response from the static displacement. So the meaning, the physical meaning of the DAF, if it's equal to 1, it means your dynamic response is exactly equal the amplitude at least. The dynamic response, the amplitude of the dynamic response of your building exactly equal to the static response. But if the DAF is greater than 1, it can be 2, it can be 3, 4.5, 6.7, that means your dynamic response will be 4.7 or 5.6, or is that magnification on the static displacement. Okay, how much your dynamic response is greater than static response is explained by this DAF. The same thing if your DAF becomes something like a 0.1, 0.2. Which means that the dynamic response of your building will be smaller than the static response. Then the case that if you apply the same amount of force to your building statically, my dynamic response of the building smaller than that. So that's why the DAF has a big name. In many design code, they ask the engineer to compute this DAF. When they want us to design the building, the bridge, and use this number, DAF, multiply with the static displacement or the static internal force, and design the building accordingly. For example, if I design the bridge under the American design code called the ASHTO, they asked me to compute the term called the impact factor. And after I compute the impact factor, maybe the number I get is something like a 0.3, 0.25. They said, your bridge will be deflected on you, and the bridge can have the maximum moment and maximum shear force equal to you push your truck on the bridge statically. I push the truck on the midspan of the bridge and compute the deflection. This is static deflection. I perform the static analysis only and multiply with this impact factor and then obtain the total response, the dynamic response, they say. They say that after you multiply your static displacement or your static moment, bending moment, with the impact factor, that is already your dynamic displacement or deflection or dynamic moment, bending moment. The taking care already the effect of the truck traveling on the bridge with some speed already, not a static truck anymore. You see, so the idea of the DF is applied in many applications as the design code I mentioned. But today we will look at the DAF or dynamic amplification factor for the case of the harmonic force. So the term is something like a 1 over square root beta, something like this, right? And this is exactly is the term is right down here. And if we look this one, okay, it's better to plot. See the plot. My building normally have the damping ratio of only 5% at most. Many of the time I have the damping of my highlight, my tall building is something like 1.5, 2%, smaller than this. This is quite high damping ratio already, 5%, as you can see in the plot. It's very high, 10 times. 10 times than the static displacement. See, the static displacement is 1, right? Remember that the DAF is just the factor multiplied with the static displacement. If the DAF equal to 1, means your building under the dynamic load has exactly the same displacement as the static system. But if your DAF is something greater than 1, in this case, you look at the peak here, equal to 10, it's very large. It implies that your dynamic response of your building is 10 times the static displacement. And this is because the frequency ratio is close to 1. It's close to 1. When the frequency ratio close to 1, there has the dynamic harmonic force that has this phenomenon called, you know, this one, I would say this is called resonance. This phenomenon is a physics phenomenon called resonance. The phenomenon that your building, your structure has the same natural, the forcing frequency has the same natural frequency of your building, or close to. It seems like many energy, very large energy are input into your building. You see the same magnitude of the force. If I don't change the magnitude of the force, remember that the force Ft is equal to F0 psi big omega t, okay, in mind. If I change the frequency from big omega to something like a 0.5 omega, let me do this. Starting from small omega. If I apply the external force with the same frequency as the structure itself, small omega, I obtain 1, right? So the beta is equal to big omega over small omega is the same thing with this. It's equal to 1.0. And this is a resonance. But if I change the frequency to be smaller, like if I change this one to 0.5 small omega, then you see the amplitude is just something like a 1.2, maybe 1.3, I don't know. And like another case, if I change the frequency to 1.5 here, I got maybe 1.0 here, close to. But when the resonance occurs, it's about 10. Very large difference. Just changing the frequency. Therefore, we civil engineer very afraid of this, very afraid of resonance, because our safety factor is not enough. And if you cannot avoid this, you have to design your building against some external force and it causes resonance to your building. I can imagine your building very, very large. You pay a lot of money for your building because the force, the displacement is 10 times than normal force. You pay more money, maybe 3 times, 4 times more expensive. I mean, the construction cost of the structure itself. So we would like to avoid this resonance. But to be effectively avoid this, you have to really understand what is the resonance is. Unluckily, it's already 11:50 something, right? So maybe I propose the quiz to next time. I will quiz you on the something close to resonance, asking you about the feeling of the thing of the resonance. But for today's discussion, I would leave 10 minutes for you to have any question for discussion together. Okay, I would like to stop my explanation here and would like you to have any question. If, okay, any questions? No?
Professor,
Yeah,
in sport,
in, right?
10 space.
You mean page number 10?
Yes.
This one, right? The last page. Okay.
With about resonance, if we increase damping ratio, can we decrease resonance?
Oh,
Right?
yes. Yeah, right. You see the plotting here, I don't explain to you yet. It's about this one, right? And this one, I think, let me see, 25%. This percent is 0.25. But believe me, 5%, damping ratio 5% is quite high already. Remember this? Remember this one, right? Yes. You see, many buildings in this world, this is European country data, 5% is here.
It's very high.
Yeah, it's very high already. So to increase the damping to, if you're talking about the tall building, this is not the tall building, okay? Forget about this. The tall building you are talking about is something like this. This is the height of the 200 meter or above. So most of them is like this, right? Just 2%, 1%, 3%. This one I plot for you is 5%. It's high or large quantities already, but it showed 10 times. 10 times than the static displacement.
What we do for this case?
That's good. What should you do if I ask you?
Oh, okay.
It's not easy, right?
You know, it's
The first is to for sure, I try to avoid this. How to avoid this? If you tell me, for example, I used to help one of the company in Thailand, but the force is harmonic in this case. Very you know the company called, the name is the Japanese TOA. You know this TOA company, the company that make the manufacture the color painting.
Yeah.
Yeah, and in their factories, there's a one Thai factory that produce some colors sent to TOA, I remember. And in the factory, something like this, is a frame, this steel frame, and on top of the steel frame is they put the color tank. It's a tank. In many floor, maybe 3, 4, 4, I forgot. But they try to put the pigment into the white color to make the color blue, to make the red, or maybe there's a lot of color, right, in their factory. So to make the pigment to the color, make the what I call is they put some machine like how to say, the swirling machine try to, when you mix the pigment to the water, right, you have to make it quite difficult for me to, they call the mixer, and if I can draw the curve, it's something like you have the machine here with the motor. This is the motor, and in this one they have some the mixer pad,
Mixture.
right? Yeah, and they try to swing like this, right? Every floor. So every time you swing like this, try to mix the color, there is a force that acting on the reaction force, acting on the floor. And this tower steel frame, they have the three, so assume they have the three mixer like this. When I finish this one, I have to drain the color to the second tank. There is the pipe to connect this to that, and the pipe connect this to that, something like this. This is the way they produce the thing. But you know, the thing, how to say, the danger is every morning they start manufacture, they just push the button, turn on the machine, and every motor will start together with the same motor. You can imagine they will go with the same frequency, right? And it make the building to be vibrate. For example, this direction very large, and they're afraid the steel frame will collapse. Do you understand what I try to explain? It's quite difficult English for me. Sorry for that. But how to solve this one? You know, very easy. They say thank you to me many times, maybe a million times, because it's easy to solve. No need to pay any money for that. Any one of you can imagine how to solve this problem? Let me try to make it sure it is a force like this, right? It's a force F1 equal to F01 psi big omega T. On the floor here is a F2 is another F0 number 2 psi big omega T, something like this, right? F number T also, I have a T4, that's another force. Very easy and very simple. And the manager of this factory really happy. After I tell him how to change the way to mix their color. Of course, they can change the frequency. But to change the frequency, you have to change the motor, or you have to, what they call is to do the one electronical circuit to control what they call it. If you play about the electric control car or airplane, you will know what they call the speed control. That speed control can change the frequency of the motor to be fast or slow, but to make sure that they're effective or not, you have to do another calibration. Is quite not easy for them. They say that they already calibrate how fast or how slow from, for example, from TOA. This is an optimum mixer already. They don't want to change the frequency, for example. And I say, why don't you do this? But before I end up with the solution I recommend, another thing is, if I would like to avoid the resonance, assume this is under resonance case. That's why the frame is moved a lot, very large displacement. Another thing, another possibility or solution is you have to change the mass. You have to change the mass of your steel frame, right? To make the natural frequency of your structure far away from the forcing frequency. Therefore, the ratio is not close to 1. That's why you can expect smaller amplitude in the DAF. You can see very clear. But this idea, I think, even though theoretically is good, but practically is not so good. Because I have to put the mass, heavy mass, on the top floor. If I put the mass on the second floor on the ground, it's no effect so much. I have to put on the top floor, right? And that has a question about the safety of the building. You increase the axial load on the columns. That is not good, right? If you're talking about the foundation, it's already constructed. How to, Any one of you can tell me how to solve this problem? Very easy.
Add the bracing นะครับอาจารย์
You do the bracing? Okay.
Yes,
one of the
to
idea,
modify the stiffness.
to have the higher frequency, I know. You do something like this, right? The bracing. Steel bracing. Is one of the good alternative, but still you pay money for this. You have to pay some money for adding the steel frame or bracing like this. That is a good idea. One of the good idea, I think, to change the frequency of the building, modify the mass, modify the stiffness. Any other idea? No. Actually, I would like to explain how I suggest them, and they say it's okay. It's very happy, but it's already noon time, so I will say this problem to you again next time.
Okay,
Let you thinking about this a week for this weekend. Sorry for that, but I want to make my student curious, to have a question in mind, to have critical thinking like this. I don't want just to show you the solution, or just to show you some example. It's better to think yourself first, and then we will keep discuss together. Okay. So next time I will come back to this slide again and telling you one of the idea I propose, and it seemed quite effective. And we will quiz you on the resonance and something like this. Okay. Okay. Thank you so much for today, and hope to see you next week, Tuesday morning. Okay.
Thank
Have
you.
a good day. Yeah. Bye-bye. Welcome.